A viewer left this comment on our tokenization and embeddings video. And honestly, that's a fair point, because embeddings only make sense once you understand what a vector really is. So let's make it simple. A vector is a position in space, and an embedding is a learned position for a token in meaning space. That's the whole idea. So if we start with one number, for example 5, one number can place something on a line. And we can assume that this object is at position 5. So with one number, we know where something is on a one-dimensional line. Now, give me two numbers. Now we can place something on a flat map. 5 steps to the right, for example, 3 steps up. That pair of numbers gives us a position on a 2D map. And that's already a vector. A vector is a set of numbers that tells us where something is in a space. If we add more number, for example the third number, now we are in the 3-dimensional space. And we can locate that position in 3D space. So the pattern is simple. And if we use hundreds or thousands of numbers, then we are locating something in a space we cannot draw anymore. But mathematically the idea is the same. Those are positions in high-dimensional space. This is exactly what large language models uses for words. A word like cat does not get just one number. It gets a position. That vector places cat somewhere inside the learned meaning space. And in that space, nearby positions usually mean related ideas. For example, cat, dog, kitten. Or if you have car is far from cat and dog and kitten. It's not because someone manually drew that map, but because during a training, the model adjusts these positions again and again. So when you are training the large language models, all those positions in the embedding table map, they're really random numbers. And during training, this table will be built by adjusting these numbers into the correct values to get the error down. So at the end, words that are useful in similar contexts get pushed closer. Words used in different contexts drift farther apart. So the model is not memorizing a dictionary, it's building a geometry of the language. That is why vectors are powerful. Once words have positions, the model can compare them. It can ask how close is cat to dog, or how far is king from banana, which words point in similar directions. This is the bridge between language and math. Humans think in meaning. Neural networks compute the numbers. Vectors turn meaning into positions that math can work with. Now let's connect this back to tokenization. When you type a sentence into an LLM, the model first breaks it into tokens. There are different tokenization methods, and a lot of models, they use different methods to calculate these tokenizations. You can actually go to this website and test different tokenization methods and see how they actually chunk these words to create different tokens. But for our video, we use a simple method just like this. The cat, sat, and dots, they're in different tokens. And we assume that between each token there's a space, of course. Then each token becomes an ID. But you need to be careful, this ID is not the meaning. It's just an address. It's like a row number in a table. The model uses that ID to look up the tokens vector in the embedding matrix. And this ID is only usable for models because models do not see language, they see numbers. So the model uses that ID to look up the tokens vector in the embedding matrix. So you have token ID, then embedding matrix, then vector position. So that vector is embedding. So an embedding is the learned vector position of the token. From that moment, the model works only with vectors. Self-attention compares vectors, for example. Transformer layers update vectors. And each token's position changes depending on context. For example, the word bank starts with one embedding, but inside the sentence river bank, the transformer moves its representation in one direction. Inside bank account, it moves it in another direction. So the starting embedding gives the token an initial position. Then the transformer refines that position based on the surrounding words. At the end, the model takes the final vector and turns it into a scores for possible next tokens. So when we say AI turns words into vectors, we are really saying that AI turns words into positions in a learned meaning space. And once words have positions, the model can compare them, move them, combine them, and use them to predict what comes next. So remember this, a token is a piece of text and token ID is just an address or identity of that text, which model could understand. A vector is a position in a space, and an embedding is the learned position of the token in meaning space. That is why AI turns words into vectors, because math cannot operate on meaning directly, but it can operate on positions. I hope that clarifies the question, and if you want to watch the embeddings and tokenization video, I'll put the video here. Until the next video, good morning, good afternoon, and good evening. Bye.